Hello, it's Mr. Kaladi here, and today we're going to go through section 5.1, which is about work. And this is the first section from our energy chapter. Work is something that is an important concept that we tend to forget, but work is when I give energy to something else. Now, in this section, that primarily involves pushing a box or pulling a box. So when you push a box or push anything, you're transferring some energy to that box. So we have a formula: work equals force times cos theta times the displacement, where theta is the angle between the force and displacement. You'll notice that these two quantities, F and delta D, don't have arrows on top. That means that we're not using the vector, we're just using the magnitude or the number part of the value. And work itself is also a scalar, it doesn't have a direction. So let's go through and see how this works. Let's say James is pushing a box 22 meters forward using a force applied of 62 newtons forward. Calculate the work done by James. For these three examples, we're going to just draw out all the forces involved. So our force, we're not really going to do a free body diagram, but we'll write that the force applied here is 62 newtons. And then we have the displacement. Well, the box travels in the same direction, so 22 meters. So we're going to go delta D equals 22 meters forward. Okay, now when you look at these two arrows, they're in the same direction. So if I were to plant this on top of this, the angle between them, well, there is no angle, they're the same. So theta, the angle between them, is 0 degrees. I'll just put here, they're in the same direction. So it's kind of an easy one. So now when I use the formula, work is equal to F cos theta delta D. I plug in my values, so I have 62 cos 0 and then 22. Notice I don't need to worry about direction. The formula will deal with direction for me. Let me get my calculator out. Now, first of all, what's cos 0? Let me just do that separately. Cos 0. Oh, it's 1. Okay, so 1 times 62 times 22. And that gives me an answer of 1364, and the units are joules. That's an amount of energy. You can think of joules like calories. You know, if you eat an apple, you ingest some calories that give you energy to do physics work. Joules is another form of energy. When you eat an apple, you get a bunch of joules that you can use to do physics work. So 1364 joules, and it's positive. Let's look at part 2. As James pushes the box 22 meters forward, a friction force of 12 newtons acts backward on the box. Calculate the work done by friction. Okay, well, the force of friction is acting in this direction, right? Force of kinetic friction is equal to 12 newtons backwards. And the displacement, well, the box is going forward, so the box is still going in this direction. Delta D is equal to 22. Now, let's say I were to plant this on top of this. Well, this vector goes this way. If I were to plant this on top of it, I would actually draw a vector out that went all the way around 180 degrees. Maybe I can draw this over to the side here. I have delta D like this, and I plant the other one at the same point. This is FK. The angle between them, we would say then, is 180 degrees. This, again, a shortcut would just be to say, well, they're in opposite directions. So, okay, let me use my formula. Work is equal to force cos theta delta D. So my force in this case is 12. Remember, I don't need to use a negative or anything. The formula is going to compensate. Cos 180. And then the displacement is 22 still. Okay, now I'm going to take my calculator. So cos 180, what's that? Oh, it's -1 times 12 times 22. That gives me -264 joules. So in this case, example 1, James pushed the box. He gave 1,364 joules of energy to the box. Now friction is acting in the opposite direction. So as the box moves forward, friction is taking away 264 joules of energy from the box. We'll learn later that usually when energy is transferred to friction, you see it in the form of heat. That's why when you rub your hands together, the friction makes your hands warm. So we're losing some energy to heat. So there's a difference between positive work and negative work. Positive work is when these two vectors are in more or less the same direction, and negative work is when these two vectors are not in the same direction. Now we're going to get some in-between cases. For example, James' brother pulls a box with the same force applied of 62 newtons at an angle of 25 degrees above the horizontal. So his friend or his brother is pulling the box in this direction. So this is FA, and that's 62 newtons, but it's at an angle of 25 degrees. Now the displacement we know is 22. Okay, now if I put these on top of each other, well, it's pretty clear to me the angle between them is 25 degrees. So let's use the formula. Work is equal to force cos theta delta D. I'm going to sub in my numbers. So I have 62 cos 25 delta D, which is 22. Let's type this in. Cos 25, which is, it's a number smaller than 1, times 62 times 22. So I get 1,236 joules. Remember, there's no direction. So what do you notice? Well, it's still positive work, but it's less than the work if they're in the same direction exactly. So you can see once I have some sort of angle, so they're not exactly in the same direction, my amount of work goes down. And you can imagine that as the angle gets more and more steep, and the angle between them is larger and larger, then there's actually going to be less and less work done. So hopefully that gives you an idea of how this formula works. You can see the formula helps you avoid having to think about direction too much. Let's continue on to 2 more examples. Make sure you go through carefully the section about zero work. There are 3 cases where you have zero work, and you got one of them, the last one especially, is a little bit tricky. Okay, so we have a puck of mass 0.17 kilograms is sliding along the ice. Eventually, after traveling 13 meters, the puck comes to a stop. Here's the coefficient of static friction, or kinetic friction. Calculate the force of friction. Okay, well, the first thing we can do here, so I'm going to write example 2. So the force of friction. Oh, well, this is something that was from last chapter. I mean, if you had to draw a free body diagram for this puck, there's a force of gravity acting on it. There is a normal force acting up. And then there's just kinetic friction that's slowing the puck down. Someone had hit it a long time ago. Eventually it's going to slow down because this is an unbalanced free body diagram. To find Fk, I would use the formula mu k Fn. However, I don't know what Fn is. Oh wait, I do. I know that the magnitude of Fn is equal to the magnitude of Fg, which is equal to mg, which is equal to, let's write those things out. The mass was 0.17 kilograms, and mu k is 0.22. So I end up with 0.170 kilograms. Oh, I don't need to write kilograms usually. And 9.8 meters per second squared. I multiply those two things together. 0.17 times 9.8. Now remember, because I don't have the arrows on top, we know I'm just dealing with scalars. I know that the value of Fn and the value of Fg are the same because they're balanced. Now I need the value, not the vector, but just the magnitude that I plug into this formula. I multiply it by 0.22, and I get 0.036652. That is the force of friction. So therefore, the force of friction is 0.37 newtons, and we'd say backwards, right? This is where we do have to put a direction at the end, and you have to use your free body diagram and your brain to kind of figure out what direction it is. Now, to find the work done by friction, well, remember, work is force cos theta times delta d. Do we know delta d? Oh, I forgot to write it out, but yeah, it travels 13 meters. I know delta d is 13 meters forwards from my question. If you want, you could go off to the side and just do this again. We know Fk looks like this. We know delta D looks like this. So we know the angle between them is 180 degrees. They're in opposite directions. Let's plug those numbers in. So we have 0.36652. Notice that I'm not using the rounded value for my answer. I'm going to use the unrounded value. That gives me a more accurate answer. Cos 180. And then delta D is 13. So let's multiply all these things together. So this 0.36 times cos 180, times 13. And there we go. Oh, I got a negative number. Does that make sense? Oh yeah, that's right, because friction's acting backwards, so I should get a negative work. Remember, think that friction is taking some energy from the puck. So therefore, the work done is negative 4.8 joules. We don't have a direction for work. Work is a scalar, so it just has a negative in front, and a negative tells us something. It tells us that work is going, or that energy is going away. And it's two significant figures. Okay, one more question here. A crate is being pulled with a force of 450 newtons at an angle of 38 degrees. There's also a friction force. Calculate the net work done on the crate. Okay, so let's go down here. We're going to get example 3. I'll just kind of draw this over here. So you have one force, which is this force. This was what? The force applied. And that is 450 newtons. And that's at an angle of 38 degrees. If it helps, I think it's a good idea. The crate is being pulled forward. I think we forgot something in this question. I think we forgot the net work done on the crate if it is pulled for 22 meters. Oops, forgot that. Okay, so now we know that the force applied is 450 newtons at 38 degrees, and we know the displacement is 22 meters forward. So for this, I know that my theta is 0 degrees. So my work from my force applied is my force applied cos theta delta d. Force applied is 450, cos 38, displacement is 22. So I have 450 times cos 38 times 22. And it's no surprise that this is positive work. Okay, now the other force is the force of friction, and the force of friction is acting this way. So it's 125 newtons, even though the displacement is this way. We know from our previous questions the angle here is 180 degrees. So when I add up the work from friction, this would be the force of friction times the theta. Oh, this would be K. Should put my subscripts here. And this is delta D. I'm going to sub in my values, so I get 125 cos 180 times 22. Okay, let's do this. 125 times cos 180 times 22. And I get negative 2750. Okay, so there's the work done by the person pulling the box. There's the work done by friction. You can see that this is a larger value. Now when we say net force, well, hopefully you remember the idea of, net work. Hopefully you remember the idea of net from when we did net force. This means add up. Net force meant add up all the forces. So net work means net work means add up all the work. So I'm going to have WA plus WK, my applied work and my friction work. 7801.306 and minus 2750. Notice that this is a lot easier because we don't have to worry about direction. So I'm going to just add to this 7801.306. So my final answer is 5051.306. So therefore the net work is, okay, this was good to 2 significant figures, this was good to 2, so my final answer should be good to 2, so it'd be 5.1 times 10 to the 3 joules. And of course, yeah, when I look at this number, the 0, yeah, it's telling me to round up to 5.1. There we go. So that's the idea of work. It's a little bit of a tricky question or a tricky concept. Make sure you go through the homework questions. There's some really interesting ones in the textbook. And we'll see you next time.